Hey everyone, back to a new awesome video, and today we're gonna continue with our series about electricity and magnetism. Today we'll introduce the concept of current. First we will define it. After that we will define an auxiliary concept which is current density, and then we'll be prepared to introduce Ohm's law. So let's start. Great. Imagine that we have a cylinder or some sort of area in space in which charges are going through. Then, if we put a charge counter in here in this area, and let us know this area, if we put a charge counter which measures the amount of charge that goes through this area at each point in time, then during a certain interval of time, and we let this run for a time interval delta t, we're gonna have that current I is gonna be defined as delta Q, which is the charge that this has measured, that has gone through in this direction. Obviously, positive charges count positive, negative charges count negative, divided by delta t. And we realize this has the form of a derivative if we let time interval go to 0. So we would have that I equals dq dt over some area. Note that current also has a direction, which doesn't appear here because it's not a vectorial quantity, but it does have a direction. In this case, the direction of current is always equal to the movement of positive charge carriers. In an analogous situation with negative charge carriers, current would point in the opposite direction to these charge carriers. One last thing to take into account is the units of this new magnitude. In the international system, the current is a unit of amperes, which is one of the 7 fundamental magnitudes that we have. And with respect to this definition of current that we have in amperes, which we see that it's equivalent by this definition to coulombs per second, we define coulombs to be amperes times second. And that's some of the most important things you need to know about current. Great. Our previous definition of current was good. However, at the scales in which we work at, the world tends to be more continuous rather than discrete. So having a counter of some sort doesn't really make sense. In this context, we introduce current density, which transforms this rather discrete setup into a more continuous one. Imagine that we have a charge, positive charge, moving with velocity v. And we want to measure the current that is going through this surface. Then we need to define some quantities. N, which is the charge density per volume, Q, which is the charge that one specific charged particle has, and we know that I equals delta Q over delta T. Then we also know that the amount of charge that is going to go through here is going to be equal to the amount of charges that we have in this volume, the amount of charge per volume, times the volume that has time to move across this area, which is going to be equal to the area times some length, which is the length that the charges may have moved, which is another thing that B times delta T. Therefore, we conclude that with this being the volume, I equals NQV times A. Taking this into account, what we see is that we can define some quantity we're going to call J, and it's going to be our current density, and we'll make it vectorial such that it's equal to NQ times V. This quantity represents how charges move, taking into account the amount of charges in all over the place and how fast they are moving, to take into account how many of them are going to cross over here. And to calculate this density, what we're going to do is to take a surface integral over this area, and that will give us that I equals over the area A of J dot dA. And this orientation, this vector is important because if this dA vector is pointing outside and it's pointing in the same direction as our J vector, we'll get a positive current. If this area vector is pointing towards the inside, we'll get a negative current, and that's what allows us to find the current direction. This definition is really useful, and similarly how charge density was useful when dealing with electrostatics, current density will be very useful when dealing with magnetostatics and in general with electromagnetism. Alright, now we're ready to introduce the macroscopic version of Ohm's law. Imagine that we have some sort of conducting or semiconductor material, and we have this cross-section of length L, which is being applied an electric field, or is experimenting an electric field. This, of course, generates that the voltage is not going to be the same at both points, at the edges. So we're going to have a voltage here, VA, and VB. Then we know that if this material is not a complete insulator, we're going to have some charge movement, which is going to generate some current density. Therefore, we're going to experience some current density. Then we know that these two variables must be related. And in fact, experimentally, we can determine some coefficients that are called resistivity and conductivity, for which each material relates these two quantities. Specifically, we're going to have that the electric field is proportional to the current density by this constant called resistivity of the material, and this is the other way around, in which we call this constant conductivity of the material. It's pretty easy to observe that the conductivity is another thing than the reciprocal of the resistivity. These two statements over here is what we denote as macroscopic Ohm's law. However, these expressions aren't really useful when dealing with circuits, as we'll do in our following videos. Therefore, we want to somehow relate these coefficients with the voltage difference and different other parameters. We know that the voltage difference, delta V, is equal to the integral from A to B of. However, in this case, E is constant all throughout our cross-section. Therefore, we can take it out of the integral, and all that is left is a path integral from here to here on this direction, which leaves us with E times L. With this E being the magnitude of our electric field. Then we know by this equation how this is related to the current density, and we're going to have that this is going to be equal to your L J, and it has to be the magnitude of these vectors. We're using the magnitude of our other vector. Similarly, we also know that our current density is going to be constant throughout this cross section, through the entire part. Therefore, we know that in this equation, we can take out our current density and just integrate over the area, which is going to give us JA. Hence, we can substitute this expression in our expression with the delta V. And this is going to give us that the delta V, the change in voltage, is going to be equal to. Then, in here, we find this special quantity that is relating voltage difference and current, which are really important quantities when dealing with circuits. Therefore, this quantity deserves a special name, and as it is proportional to the resistivity of the material, we're going to call it resistance. Therefore, we end up with an expression of the form delta V equals IR, which is the common expression that we're used to see for Ohm's law. That is all for today. I hope that you understood everything and that you got a sense of how current density relate to each other, and also how we can use different properties that we already know about electrostatics and our surface integrals, etc., to relate different quantities. You will see in action how this is very useful to deal with circuits in our next videos about circuits. Any doubts left, you may ask them in the comment section and I'll try to answer them in the best way I can. Remember to like the video if it was the case, subscribe to the channel and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!